Quasicrystals. From impossible theory to commonplace discovery for decades, quasicrystals were dismissed as a mathematical curiosity structures so bizarre they couldn't possibly exist in nature. Today, these impossible materials are turning up in the most unexpected places, from atomic bomb test sites to meteorites, challenging our understanding of how matter forms and evolves. The story of their discovery isn't just about a scientific breakthrough. It's a reminder that the universe often defies neat categorization. The long-held impossibility crystals, the building blocks of our material world, have always followed strict rules of symmetry. For centuries, scientists believed that only 230 distinct crystal structures were possible, each based on repeating atomic patterns. This framework excluded structures with forbidden symmetries, like five-fold or seven-fold rotational order, because they couldn't fit together without gaps or overlaps. The idea that such structures could exist was first proposed in 1983 by physicist Paul Steinhardt and his student Dov Levine. Their theory suggested that quasicrystals could form solids with non-repeating atomic patterns, creating a kind of disharmony in space. This was initially met with skepticism, but in 1984, materials scientist Daniel Schechman proved them right by synthesizing a lab-grown alloy with a five-fold symmetry. The Nobel Prize followed in 2011, though many still saw quasicrystals as unstable anomalies confined to controlled environments. Beyond the lab, quasicrystals in the wild Steinhardt wasn't satisfied. He believed that if quasicrystals could form under laboratory conditions, they must also exist naturally. Teaming up with geologist Luca Bindi, they began searching for these materials in the real world. One of their first discoveries came from a meteorite called Quasicrystals, found in a remote region of Siberia. This meteorite contained the first natural quasicrystal ever identified, proving that these structures could form outside the lab. The team continued to push the boundaries, exploring extreme environments where quasicrystals might survive. One key insight was that high-energy events, like asteroid impacts or explosions, might create the conditions necessary for their formation. This led them to an unlikely source, the remnants of the first atomic bomb test, known as trinitite. Samples collected from the Trinity site contained not only glass, but also the first human-made quasicrystal, formed by the intense heat and shock waves of the explosion. The unexpected stability of quasicrystals for years, it was assumed that quasicrystals were inherently unstable, destined to break down into conventional crystal structures over time. However, recent research is challenging this notion. Using new modeling techniques, scientists have shown that some quasicrystals can be genuinely stable, capable of surviving for billions of years. This stability, combined with their unique atomic structure, makes them valuable witnesses to the violent events that create them. A new window into cosmic history, the discovery of quasicrystals has implications far beyond materials science. They could serve as markers of cosmic impacts during planet formation, offering clues about the early history of the solar system. Researchers are now examining samples from meteorites and even the Apollo missions, hoping to find evidence of quasicrystals that could reveal more about the conditions on ancient celestial bodies. The search continues, with scientists sifting through micrometeorites, volcanic glass, and even samples from Antarctica, where space dust accumulates in ice. The ultimate goal is not just to find more quasicrystals, but to understand how they form, what they can tell us about the universe, and why these impossible structures are turning out to be surprisingly common. The ongoing discoveries suggest that quasicrystals are not just a scientific curiosity, but a fundamental part of the natural world, waiting to be found in the most unexpected places.